Welcome to the Unit 3.2 and 3.3b Drawing Lewis dot structure notes. So there are two parts for these notes. The first part is part 1 is drawing Lewis dot structure for ionic compounds. And what I have listed here, the 3 steps, and then some examples, 2 examples. Okay, so the first step is to draw the Lewis dot structure of all the atoms. And given something like Na2O or AlCl3, so aluminum chloride, sodium oxide. Sodium oxide has 2 sodium atoms, so I write them both down. And since they're in group 1, they have 1 valence electron, so that I just draw a single dot. Whereas oxygen is in group 16, it has 6 valence electrons, so remember, you give each corner 1 before doubling it up, and this is its Lewis dot structure. I repeat the same thing for aluminum chloride. So aluminum has 3 valence electrons, and each chlorine has 7. These are their Lewis dot structures. And notice that I need to do it for all the atoms. So this has 3 chlorines, so I did Lewis dot structure for all 3 chlorines. Step 2 is to transfer electrons from metal to nonmetal. Metal will get an empty shell when that happens. So remember, atoms want to gain or lose electrons until they have a full valence shell by losing all of the electrons in its current valence shell. The metal then has the next shell down, the metal that's in the metal's electron shell, is a full shell. So by losing all the electrons in its current outer shell, the next shell down becomes a full shell. So that's why sodium will give its electrons away to oxygen. All right, and you have to do that. So you have to make sure that the metals lose all of their valence electrons. And the non-metal, the oxygen, needs to gain enough to get a full shell. Since it had 6, you better make sure that in this case, it gains 2. So the same thing we'll do for the aluminum. That's our metal. It's going to give its valence electrons away. So that's step 2 to transfer. The last step is to add appropriate charges and to put brackets around your nonmetal. And the reason why we put brackets around the nonmetal is because the nonmetal has all these valence electrons on it, and you want to make sure people know that those valence electrons belong to the nonmetal. So we put brackets around those. You can also put brackets around the metal, but you don't have to. Now, when I say appropriate charges, what I mean by that is that each sodium here lost 1 valence electron, so they would have a +1 charge. And the oxygen gained 2 electrons, so it would have a -2 charge. Remember, if you gain electrons, you're going to have a negative charge, and if you lose electrons, you'll become more positive. And there's 2 ways that I can write this. I can write this by writing out each of the ions, and I like to alternate cations, positive charges, and anions. The other way you can do it is you can use a coefficient in front of any ion that you have more than one of. So in this case, there are 2 sodium ions, so I put a 2 Na+. And then in brackets, I have my oxygen with its octet and a 2- charge. Here's the same thing for aluminum chloride. So in this case, since I have 3 anions to alternate, I kind of made this sort of T-type shape. In the middle here, I have aluminum that's a +3. And each chlorine has a -1 charge. And remember, they're in brackets. So I can write it this way, or I can write it as aluminum, and that should be +3 or 3+. That's a +3, and 3Cl -1. All right, so that's for ionic compounds. I'm going to zoom this out, so if you want to just copy the information down, you can. Pause the video if you need to. All right, now let's take a look at what we do for covalent molecules. Okay, so covalent molecules, they're made up of 2 nonmetals. Right? And the steps are going to be different because a couple of reasons why they'll be different. One, in a covalent molecule, electrons are shared. They're not transferred. In ionic, they're transferred, and that's why we drew those arrows. Okay? And also, because they are shared and not transferred, when we make our covalent molecules, for the most part, you're not going to have any charges. Now, if your chemical formula for your covalent molecule has a charge, then your Lewis dot structure will have a charge as well. But that's the only time that you should have a charge. Everything else should be neutral. And we'll talk about formal charges, which are a little different later. They're not actual charges. Okay, so here are the steps. First, you're going to count the total number of valence electrons. So, for example, in NH2F, nitrogen is in group 15, it has 5. Each hydrogen is in group 1, it has 1. And fluorine is in group 17, it has 7. So 5 plus 1 plus 1 plus 7 gives you 14. And I'm going to do that for the other chemicals as well, CH2O and C3H6. All right, once you have that, the next step is to draw the skeletal structure. Now, the skeletal structure is essentially the central atom, whatever your central atom is, connected to what's called the terminal or all the other atoms with single bonds. So to do that, the first thing you need to do is pick your central atom. Now, your central atom will be the one that's usually the least electronegative. And if you recall, when it comes down to electronegativity in the periodic table, right? Electronegativity increases going to the right and decreases going down. So if we're saying the least electronegative element, we're looking at one that's in the lower left-hand corner. All right, so with that being said, nitrogen, which is around here somewhere, and here's fluorine, nitrogen is going to be the least electronegative. And the other thing I should note is that hydrogen cannot go in the middle, because remember, hydrogen, its valence electron is in group 1, or the first shell, not group 1, the first shell, which can only fit 2. So that means that hydrogen can only form 1 bond. Each bond is a pair of electrons. So hydrogens always have to go in the end. Okay? All right, so we pick our central atom and we connect everything else to it with a single bond. So if the central atom here is nitrogen, I'm going to connect the hydrogens and the fluorine to it with a single bond. I do the same thing here. In this case, carbon is less electronegative than oxygen. And again, hydrogens have to go in the end. So this is my structure, carbon in the middle, connect oxygen into the hydrogens. In this last case, C3H6, the carbons would go in the middle. Now there's 3 carbons there, so which one goes in the middle? Well, in the case where you have something where there's more than one central atom, just connect the ones that are central atoms together in a straight line first. I connected these carbons, and then I attached on my 6 hydrogens. And this, by the way, is an error that I added too many hydrogens. Okay, so now the next part is to use the remaining valence electrons to give everything an octet. Okay, so what do I mean by that? Sorry, this is a bit crooked here. In the case of the nitrogen, if we go back up to our skeletal structure, nitrogen already has 2, 4, 6 electrons around it. It needs 2 more to get an octet. All right, so the nitrogen needs 2 more. Each hydrogen, is fine, because remember, hydrogens don't want to have an octet. They're good with 2 electrons, and they have their 2 electrons, so they don't need any. And the fluorine itself needs 2, 4, 6. To get an octet, it needs a total of 8 electrons around it. It already has a pair from the bond, and it would need 6 more. So that means that in total, this structure needs 8 electrons. Well, let's figure out how many we have. We started off with it in the structure 14 valence electrons. To make my skeletal structure, I use 6. So 14 minus 6 means I have 8 left. In the case where the amount that you need to give everything an octet is equal to the amount that you have, then you're going to have all single bonds. So all I do is I just add on the lone pairs in that case. On the other hand, if I look at this one here, going to this structure here for CH2O, if we look at the carbon has 2, 4, 6 electrons around it. So right now it's going to need 2 more to get an octet of 8. The oxygen has only 2 electrons around it, so it's going to need 6 more. And each of the hydrogens are good. They already have their 1 bond. So this needs a total of 8 as well. However, this is how much we need, but I only have 6, because remember, I started off with 12 in this structure, and I use 6 to make my skeletal structure. So 12 minus the 6 means I have 6 remaining. So in this case, I have less than what I need. And so that tells me I'm going to have to do a multiple bond or a double bond. And that's how I got this. So by putting that double bond in here, the oxygen has 2, 4, 6, 8 electrons, and the carbon also has 2, 4, 6, 8 electrons. So they're both good. Okay, the last In the last case, it was something similar. So in this case, when I counted it up, I saw that I needed 2, 4 electrons for the carbons, and the hydrogens were good, but I only had 2 remaining, so I had to do a multiple bond here as well. Okay. Last steps is to check the structures. So, and I'll go back in case you need to take a picture of that in a moment. So to check the structures, we want to make sure everything has an octet, and we're just counting the pairs of electrons around each atom. Remember, except for hydrogens, they're good with just 2. So I did that here. And then for formal charges, the structure should have the least amount or reduced formal charges on each atom. In this case, we count the number of valence electrons minus the number of bonds attached to that atom minus the number of lone pair electrons. So for example, the formal charge on nitrogen. Nitrogen has nitrogen group 15, so it's 5 valence electrons. I start there. And then the number of bonds attached to it, 1, 2, 3 bonds. So I'm going to subtract 3 from that. And the number of lone pairs, electrons, I got to count each dot in this case. 1, 2, so it's minus 2. It gives you a total of 0. So this has a formal charge of 0. Same thing for fluorine. It has a formal charge of 0, 7 valence electrons, minus 1 from the bond that's attached to it, minus 6 from the lone pair electrons. Okay, so that is it for this video. I'm going to go back so you need to pause to copy the information for covalent molecules. And if you need to pause to copy the information for the last page, you can do that as well. All right, I hope you found this video helpful. Have a quality day.